Hello and welcome to this lecture. So we saw previously that if you use this orthogonal projection idea, you can do solve problems like approximating a function with another type of function. Okay, any function with a linear combination of other functions you can do. So now one of the functions that appear all the time in electronic systems is sinusoids. In fact, sinusoids appear everywhere and they're very important functions. So what about sinusoids? I mean, the sinusoid seems interesting. Can we do projections onto sinusoids and what happens there? And that will lead us to this very important topic of Fourier series. It turns out Fourier series is nothing but projection onto a bunch of sinusoids. Okay, so we'll see that in this lecture. Okay, so first thing is we will pick our own favorite little L201. You can also pick other intervals here. It doesn't change the description too much. I'm going to pick 01 just as an example. So I'm going to pick L201 and I'm going to consider an orthonormal set of sinusoids in this L201. Okay. So first of all, I'll consider a bunch of sinusoids. Well, okay, one you may say is not a sinusoid, but it's sort of, you know, if you at some level you can accept one we'll take as a sinusoid, and then I will look at a whole bunch of cos functions and sine functions. Okay, so I'll plot these things later for you, but for now let's just take these plots and move on. Cos 2 pi t, cos 4 pi t, cos 6 pi t. You can see I am doubling what's inside there, right? It's 2 pi t, 4 pi t, 6 pi t. Likewise, I'm also doing sine 2 pi t, sine 4 pi t, sine 6 pi t. Okay, so if you think of 0 to 1, from 0 to 1 you have one cycle of cos here, you have two cycles of cos here, it's three cycles of cos. For sine, likewise, from 0 to 1 you have one cycle of cos, sine, two cycles of sine, three cycles of sine. That's what it means, 3 cycles, 4 cycles, sine 8 pi t, 10 pi t, so on, cos 8 pi t, 10 pi t, so on. Very interesting result about these functions is any two functions in this set are orthogonal to each other. Okay, so you multiply any two functions and integrate from 0 to 1, you will get 0. Okay, so we've seen this before. We saw it in the context of finding inner products and all that. So this set is an orthogonal set, and in fact, remember, this is an infinite number of functions. You can keep going on and on and on in cos and sine. How many ever you start adding, any two will always be orthogonal. Okay, so this is the power of the infinite dimension, right? So when you have finite dimensions, you know, after a point everything becomes linearly dependent, linearly orthogonal, right? So here you can keep going on and on and on, they'll forever be orthogonal. Okay, so it's a very interesting thing. Okay, so now you can make it orthonormal also. The only thing that's missing is normalization, so you have to find the norm. So it turns out the norm of any of these guys, in fact norm of 1 is actually 1. Okay, norm of 1 is 1, but norm of all these other cos and sines are all half. Okay, so this is very easy to see, and you can integrate very easily. So if you integrate, say, cos 2 pi t, you have to integrate cos square 2 pi t, right, for finding the norm. But cos square is 1 minus cos 4 pi t divided by 2. Okay, so that half is what remains here. The minus cos pi 2 pi t will go off to 0, so the half you get. So that cos square to cos 2t, cos square theta is 1 minus cos 2 theta by 2, right? So that by 2, that 1 by 2 shows up here. So you get the half here, you'll get the half here also. Okay, so what happens now is, so when you normalize, all of these guys have to be divided by the norm. The norm is 1 by root 2. So when you divide by 1 by root 2, it becomes multiplication by root 2. So this, once you multiply by root 2, and 1 remains, of course, 1 by itself, because the norm 1 is 1, right? So you integrate from 0 to 1, 1 squared, you just get 1. Okay, so there's no problem there. So that remains 1, but all these other guys get multiplied by root 2. This is just a normalization, simple enough, but if you do that, you get this orthonormal set. Okay, so this is an orthonormal set of sinusoids in my L201 with respect to the inner product that we defined. Okay, so yeah, once again I want to remind you, this is an infinite number of orthonormal vectors. That's what you have. So this is the orthonormal set of sinusoids. Okay, so here's a plot, and I think forget about the scale. I think the scale is a bit wrong here, but this is a plot of cos 2 pi t. So you see that one cycle of cos, and cos 4 pi t is 2 cycles of cos, cos 6 pi t is 3 cycles, and cos 8 pi t is 4 cycles. And it's amazing that any two of these, if you multiply and integrate, you will get 0. Okay, so in fact, that's the nature of these functions. And here is sine. Sine starts at 0 and ends at 0. Is one cycle of sine, sine 2 pi t from 0 to 1. 2 cycles, 4 pi t, 3 cycles, 6 pi t, 4 cycles, 8 pi t. Once again, any two of these guys, okay, not the same guy, any two of these guys, if you multiply and integrate, you will get 0. The same guy, if you multiply with itself and integrate, you will get half. Okay, so that's the very nice property of this, which you might find, I mean, at least I find it intriguing that these functions have these very cool properties. So this is just a plot. You can keep increasing. I mean, if you can go from 8 to 16, 32, I mean, just to get to very high numbers, or you can go to 8, 10, 12, 14, etc. The number of cycles will keep on increasing, the sign will start shrinking a little bit, the frequency goes up, time period goes down, all these kind of definitions one can make. Okay. So now let's look at projecting onto the span of sinusoids. Okay, so what do I mean by that? So I have my x of t, some function or signal x of t. Let's say it's in L201. I'll pick L201 just for convenience. So x of t is in L201, and I'm going to project this x of t onto the set of sinusoids. Now I'll stop at k here. Of course, you can pick k to be arbitrary, right? So I start with 1. And then I have cos 2 pi t sin 2 pi t, then I have cos 4 pi t sin 4 pi t, so on till cos 2 pi k t sin 2 pi k t. K will be some integer, k could be 0, which means there will be only 1 here. If k is 1, you will only have cos 2 pi t and sin 2 pi t here. If k is 2, you will stop at cos 4 pi t sin 4 pi t, and you can go on till any k. K 5 means you will stop at cos 10 pi t sin 10 pi t, like that, right? So this is defines a span of a bunch of sinusoids. It defines a subspace, and I might ask a question: the arbitrary x of t that I have in L2, how close is it to these sinusoids? Okay. Now you may wonder, why is this interesting and important, and we'll come back and look at it in a later lecture. Why are these sinusoids so important? Because they turn out to be very important functions in many linear systems. So we want to see how to express x of t as a linear combination of sinusoids. Okay. And this you may not be able to exactly do, but we will use our idea of projection to come up with the closest combination of sinusoids, which is going to be sort of representing x of t in some sense. Okay. And of course, as I increase k, maybe I can expect the representation to be better and better, right? So because I'm using more and more basis function. Okay. So that's the projection we're talking about. So what is the projection? We know how to execute this projection. This is an orthonormal basis. So you just do inner product with 1 here, cos 2 pi t here, and 2. How did I get this 2 here? Of course, you have to do inner product with x comma root 2 cos 2 pi t, and then multiply by root 2 cos 2 pi t again. This root 2 and root 2 will multiply and become a 2. Okay. So hope you see that here. So I wrote this like this. Okay. So I go all the way up to k and I stop. This function I'm going to call as xk of t. What is the property of xk of t? Xk of t is closest in this span to x of t in the L2 norm, that we have defined. Okay. So that's what this means. So this kind of a function xk of t is very, very special. It goes up to k, and it's in fact called the Fourier series or the partial Fourier series. It stops at k, so it's a partial Fourier series. As you keep increasing k on and on and on, you get the entire Fourier series. So this is xk of t. So a crucial question to ask is, how does this xk of t look as k increases, and what is going to be the connection between xk of t and x of t, right? So I'm projecting this x of t, I'm getting closer, and as I increase k, my subspace is increasing and increasing. So maybe I will get closer and closer to x of t. How close can I get is the question, right? So we may not be able to answer this very precisely in this course. So I'll just give you some intuition on how this is going to behave. Maybe in later courses, you will see how it works. Okay. All right, let's see one example. Okay, so we'll see one example. We'll take this function x of t equals t. Okay, so you might argue this itself is simple. Yeah, it is simple. I agree with you, but it's interesting to see if I can express this t as a sum of sinusoids. Okay, so this t looks like the straight function, right? And the sinusoids do up and down, up and down, up and down. As you increase the frequency, they're going up and down. How is it that you can write this x of t equals t in the interval 0, 1 as the sum of sinusoids? Okay, is it even possible? Does it even work? I mean, you know, if you project, will you get something reasonable? So that's what we're going to see, and that's okay. I mean, as far as we are concerned, we can project quite easily. So we can do inner product of t comma 1. This is integral 0 to 1 of t, and that will be just half. And then you can do that's x0 of t. I'm sorry, I'm trying to do the projection. The first projection of degree 0, so to speak, is just this half. Okay, so it says half is the best we can do here. And then x1 of t is, of course, you know, you project, you do inner product with 1, inner product with cos 2 pi t and sin 2 pi t. Now these you have to evaluate, right? So t comma cos 2 pi t is integral 0 to 1 t cos 2 pi t dt. Now that integral again involves some integration of parts or by parts and all that. Okay, you may remember that from math 1, or like me, you can go to a computing package and then throw this integral at it and it will give you the answer. If it gives you the answer, you can write it down. You will see that this particular integral actually goes off to 0. The integral t cos 2 pi t, it goes off to 0 because that's how it works. Okay, so that integral goes to 0, 0 to 1. This integral alone survives, and that integral becomes minus 1 by pi sine 2 pi t. Okay, once again, you can do this in a package, in a computing package, or you can do it by hand using integration by parts, or you will get the same answer. Okay, so this half minus 1 by pi sine 2 pi t. Okay, so initially the x0 of t is just half, the first approximation. Then once you do cos 2 pi t, you get minus 1 by pi. If you do up to 2, x2 of t, you will get sine 2 pi t minus 1 by 2 pi sine 4 pi t. Again, there will be a lot of two more dot products involved. The cos term will go off to 0, sine term alone will survive. You will get minus 1 by 2 pi sine 4 pi t. x3 goes to minus 1 by 3 pi sine 6 pi t. And now you can see that there is a pattern that is emerging. Now this pattern can be generally proven. You can do with the sine kt and then show that xk of t will be half minus 1 by pi sine 2 pi t minus 1 by 2 pi sine 4 pi t, so on till minus 1 by k pi sine 2 pi kt. Okay. So at least mechanically you can evaluate this projection. You can evaluate for any x of t the projection onto the sinusoids. Okay. Some coefficients will be 0, some coefficients will be non-zero. Okay. But how good is this xk of t? Is this xk of t actually close to x of t? You may ask, have I really succeeded in writing t as a linear combination of sinusoids or not? You might wonder, and for that I am going to plot for you. Okay, so let me just plot in this case. This is x of t equals t, this straight line here, and this is x1 of t. Okay, this half, you saw the x1 of t, right? Half minus 1 by pi sine 2 pi t. So it does this oscillation as you can expect. The sinusoid, it's just a sinusoid. It is sort of all over the place, but you can see it's close to this line, isn't it? I mean, it's sort of not deviating too much from the line. Next, I have plotted x4 of t. So notice what's happening in x4 of t. Already there are like this 4 cycles here, but then you can see how it is coming close to the line. And this is x8 of t, just going a bit faster. You can see x8 of t is even closer, okay, overall. Then you have x16 of t, it's going much closer, x32 is much closer, x64 is much closer, x128 is really close. So just to show you, drive home the point, x of t equals t is completely sort of covered up with x128 of t, except in the corners, right? So except in the corners is an issue, you can just ignore it, but in the main part of it, right, from 0 to 1, x of t equals t has been expressed very nicely as the linear combination of sinusoids by this projection. Okay, so you see it sort of approaches x of t. At most points it approaches, we leave it like that. Looking at these things more deeply needs higher bit of theory. But anyway, I want to convince you that you can take a function that looks like t, then project it onto sinusoids and write it as a combination of sinusoids. In the particular interval 0, 1, it makes sense. Okay, so this leads us to the definition of what I am going to define as the Fourier series. I should be careful here, this is the partial Fourier series. I shouldn't say it's a Fourier series, it's a partial Fourier series, but anyway, for our purposes, this is okay. The Fourier series in the interval 0, 1, I am going to define, you have a real signal, let's say x of t, the Fourier series is xk of t, partial Fourier series is xk of t, and that is this guy, a0, some constant a0 plus a1 multiplying cos 2 pi t, b1 multiplying sin 2 pi t, so on till ak multiplying cos 2 pi t, bk multiplying sin 2 pi t. So the Fourier series is about expressing some function signal x of t as a linear combination of sinusoids. How do you find these coefficients? A0 is just the inner product with x comma 1, it's integral 0 to 1 x of t dt. A1 is 2 times the inner product x times cos. You remember there was a 2 factor that came up from somewhere. So it's 2 times integral 0 to 1 x of t cos 2 pi lt. L goes from 1 to k. BL is like 2 times integral 0 to 1 x of t sin 2 pi lt, and L goes from 1 to k. So this is my definition for the partial Fourier series up to some k, whatever k you may want to pick, up to some harmonic. This k is called the harmonic, first fundamental, second harmonic, third harmonic, so on till the kth harmonic. Okay, so this is usually called the sinusoidal form of the Fourier series. There's also other forms, we can see that later. So the sinusoidal form is something you have to evaluate. So here are a couple of examples, very simple examples. If you do a signals and systems course, You will see a lot of such examples of doing Fourier series, and these two examples are very nice. I will urge you to try them. Okay, so this basically how do you evaluate those inner products, right, with the sinusoid and the cosine. If you get a general formula, you can write xk of t in terms of those sinusoids. Okay, so that's the end of this lecture. Hopefully this definition of Fourier series is interesting to you. Thank you very much.